Okay, good day to all of you guys. We'll get started. Hope I'm audible to all of you and you can see my screen, right? The answers to both the questions is yes, right? Anyone, please just
Yes.
confirm. Okay, great, great. Thank you, Ayush. So let's get started. And as usual, every day, I'll just start little bit from, little bit with keeping little bit overlap from what we discussed in the last class, so that the continuity between the lectures are kind of well maintained. So yesterday we discussed about how the electrical and the mechanical domain relationships would interact. But before that, we also saw how the charge kind of varies when we apply a force or we apply a voltage. Charge in the on the opposite faces of the piezoelectric material in which the material has been pulled, right? So, for example, we saw that. So this material we saw. So this was the polling direction. So what we saw is so this is the material in its natural condition after the fabrication has happened, and these are the charges that are there in the material. The residual charges, or you can say the characteristic charges of the material, right? And then if we apply a force or a stress in the direction as shown, we discussed why the charges would increase. So the charges would increase. As you can see, the number of charges are actually increasing if we are applying a force, because the charges would develop in a way such that the force that we are applying externally would be opposed, right? So because we are trying to stretch the material, right, in this direction, the number of charges are increasing on both the sides, because essentially the attraction between these two plates, right, is increasing because the internal electric field is becoming stronger, and that inherently is trying to oppose the force that we are applying, right? So this is the mechanical side of things. And similarly, what we saw is if we apply a voltage as shown, please note the direction of the voltage source. So actually the electric field that we're applying because of this external battery is opposite to the direction of the opposite to the polling direction, right? So easy way to kind of comprehend or remember things is if the external field is in opposite direction to the polling direction, then the material will actually deform to reduce. The delta L will be negative, right? And that also we explain why it happens, because essentially the electric field that the external battery is creating is in this direction, and the internal charges would try to move in the direction of the electric field, right? The positive charges will try to move in this direction, and the negative charges will try to move in this direction, right? So essentially these two layers would try to come closer to each other, which means the delta L will be 0. That's what we saw, right? And then what we saw are individually the domain relationships. So the domain relationships are there independent of whether the material is marked or not, right? So the first equation which comes from the Hooke's law is where the strain, capital S, is the strain, is proportional to the stress, capital T, and the proportionality constant we said is compliance. And softer the material, the more compliant it is, right? Basically, what it means is the strain will be more if the compliance is more, right? It is trying to, so basically the material will comply with the external force, right? And then the second equation we saw, which essentially is a fundamental equation of a capacitor, is D proportional to the electric field, right? where the proportionality constant is the permittivity, right? So these two equations are inherently there in any material. And then we also saw, because the material is smart, and we are talking of piezoelectric material, and we are going to look at how we are going to make a transducer out of it. There are two more equations we need to deal with, right? And we saw S is equal to dE is one set of equation. We'll get into D little bit more in details. We'll discuss this in matrix form. And similarly, in the electrical world, or on the electrical side of things, P is equal to D times D. So the inverse, so the first guy is the inverse, because why is it inverse? Because looking at the left side of the equation, right? So this is the dependent variable. So the dependent variable is mechanical, and E, which is the independent variable, essentially nothing but the input, is electrical, right? So essentially the electrical component is the input, or electrical information is the input, and the output is mechanical, right? So that's the reason we are saying that the electrical information has been converted to mechanical information, and that is the reason we call it inverse. I mean, we call it inverse just historically because this was the one that was found out later, and the direct effect was what was discovered first, right? And there also, why this is direct, because P is in the electrical domain and T is in the mechanical domain. So we are going from the mechanical domain to the electrical domain, and that's the reason we call it direct. Now, because we are talking of smart materials, we have to consider both the domain relationship and the transducer relationships to characterize the material completely, because it will then show why the material is going to have both the domain. So this side again corresponds to the domain relationship, and this side corresponds to the transducer or the smart aspect of the material, right? And then we told that, look, this is the actuator. Why this is the actuator? Just by looking at the equation, we should be able to tell why it is the actuator, because the output of an actuator is mechanical. And here again, I keep repeating this just by looking, and it's very important, guys, because looking at an equation, and this is true for any subject that you are studying. If you are studying basic or let's say analog electronics, or any equation that you are writing, right? You should be able to figure out, which is the dependent variable and which is the independent variable. And typically what we write is the output we will write on the left hand side of the equation, and that is called the dependent variable. And the input to whatever circuits or systems that we are doing, we will write it on the left side, right? That's the convention that we follow, irrespective of whether we are talking of a transducer or maybe a transistor or an amplifier, that we'll always write it in this form, right? So why is it an actuator? Because the output is in mechanical domain, and that is proportional. What we have done is we have combined these domain relationships and the transducer relationship into one, right? It's a basic simple kind of addition that we have done. And similarly, the sensor portion, the sensor, if we are using the material as a sensor, this is how the relationship will look like. And D again is in the electrical domain. And then this is again, we added these two equations. This is this side we added, and this side we added, and then we said that, okay, this is our sensor relationship, right? And then we said that, look, we brought in this concept of subscript. And the reason we brought in the concept of subscript, please note how we are using the subscript. When we are talking of an actuator, meaning the output or the dependent variable is mechanical, right? The coefficient associated with in the mechanical domain, that is what we are saying must be specified with a given electrical condition. I repeat, we are talking of an actuator. So basically the output is mechanical, right? And because the output is mechanical, we have coefficient which is associated with the material in the mechanical domain, which is compliance coefficient. But because we are treating this as an actuator, this compliance coefficient must be specified at a given electrical condition. So this E, so this is the electrical field that we are going to apply, right? So how the overall actuator is going to behave must have a mechanical coefficient specified with a given electrical condition. And that's what we denote as S subscript E, right? The compliance at a given electrical condition. Similarly, by the given, in the same, by the same token, right? If we have talked of an actuator, the sensor cannot be left far behind, right? It's the same family and we should treat them equally. So similarly, when we are talking of a sensor, we are talking of the output is in electrical domain, right? So what that means is the coefficient associated in the electrical domain, right? The domain coefficient associated in the electrical domain must be specified at a given mechanical condition, right? So T is the mechanical variable. So epsilon, the permittivity, must be specified at a given mechanical condition. So T appears here in the subscript, right? So, and this we said is the strain charge form. And we also said that there are many other forms which you look into. There are 3 other forms, right? So this is called the strain charge form of the transducer or of the piezoelectric material, right? And then what we kind of discussed is how we can measure the compliance S at a given electrical condition, right? S subscript E, how we can measure. So we said that, look, if we have a piezoelectric material with the pulling direction as shown, and we are applying the stress. So even without when the without the shorting that we have shown here, without the short also, if we have, let's say, 3 positive and negative charges on both sides, right? And then we are applying the stress, because we have shorted them, what happens is any additional charge is kind of sucked away by the wire. So any additional charge is, we are not allowing any additional charge to develop in the wire, because we are ensuring that the potential at this plate, this top plate and the bottom plate B, these 2 plates are same. So no additional charges will be appearing even though we are applying a stress. So what that means is the electric field existing inside the material because of the external, basically the external electric field. When we are talking of capital E, right, this subscript, that means it's an external, we are talking of the external environment. So we are ensuring the electric field caused by the in the external environment is nothing but 0, and 0 is also a constant, right? And instead of that, we also said that instead of 0, if it is a battery of whatever value, 5 volts or 3 volts or whatever, and we still do the same experiment, even then the same thing will happen. We will be measuring S suffix E, just that it will be at a different condition. So S suffix E will be different, right? And the point to note here is only mechanical energy stored. Why mechanical energy stored? Because any electrical energy that would have actually accumulated because we have shorted them, or because we have a battery which is like an infinite source of charge, what happens is any new additional charge that would have appeared by applying the external force is being sucked away by the battery or the wire. It kind of shorts it, right? So only mechanical energy is stored, right? And what we also said is that, look, what are the 2 electrical things that, if you look at these 4 equations, right, on the left hand side we have 2 electrical components. One is D and the second is P, the polarization, and D and P we are using interchangeably, right? We are saying that they are the same component, polarization, just that we call it in a different name. So basically it is nothing but charge per unit area the charge density, the surface charge density. And so this is 1. So D and P is 1. And we have another component E, which is the external field that we are applying, right? So whereas we are talking about the compliance coefficient at a given electric field E, we can also talk about the same compliance coefficient at a given electrical condition of constant charge. Instead of constant field, we can also talk of the compliance coefficient under a constant polarization or a constant charge, right? And let's see how SD and SE are related. So SE is compliance coefficient at constant E, right? So now we have kind of introduced and talked about boundary conditions, right? Meaning essentially when we are talking of one property or one domain characteristics. So the domain we have only two domain characteristics, right? Or coefficient associated with domain relationships are only two, right? One is compliance and one is permittivity. So when we are talking of both these coefficient, we should mention what are the boundary conditions. So when we are talking of the mechanical coefficient of compliance, we should specify what are the electrical conditions. And similarly, when we are talking of permittivity, which is nothing but an electrical domain coefficient, we should specify what are the surrounding mechanical conditions. So this is what we call as boundary conditions, right? So let's look at the electrical boundary conditions. So here again we'll look at electrical and mechanical both. We start with electrical. So we have this piezoelectric material. Again, this arrow is nothing but the polling direction. And as you can see, I just have two wires. They are open. They are like open circuited. The terminals are open circuited. And these positive and negative charges are nothing but the inherent charges that are existing on the opposite faces of the material because of polling, right? Because of the fabrication that we have done. So this is one condition, right? And in this condition, what we say is D is equal 0. Why D is equal 0? The reason is D is what? D is the displacement, right? The electrical displacement or dielectric displacement, right? So this is D, right? What we mean by displacement is the amount of charge that we are displacing into or out of the faces, right? Out of these two plates, right? The top plate and the bottom plate. Now, because there is nothing connected, right? We are not displacing any charge, right? So this can be one electrical condition. So when D is equals to 0, meaning we are not displacing any charge, and in this case, under this scenario, right? If we apply a stress, the same stress, right? If we apply the stress, right? Let me see if I have the animation. No, I don't have the animation for this. If I apply a stress, right? What is going to happen? I've mentioned it, so you can read it. Actually, both mechanical as well as electrical energy will be stored. Why both? Because when we are stretching the material is deforming, right? And because of that, there is some mechanical energy we are storing in the material itself by the virtue of stretching, right? And on top of it, because it's piezoelectric, when we are stretching the material, what is going to happen to the number of charges on these two plates? We have discussed this. If you are stretching it in this direction, what is going to happen?
It will increase.
Right. The number of charges will increase. But please keep in mind, increase or decrease is not important in this case, right? What we are saying is, if the two terminals of the transducer are not shorted, there is an electrical change that is happening on the two surfaces, right? Because of which we are saying that on top of the mechanical energy that we are storing, we are also storing electrical energy. So both electrical as well as mechanical energy will be stored. And under this condition, if we were to study the relationship of stress and strain. Strain is capital S. And under this condition, if we study the relationship of capital S with capital T, or respectively strain as a function of stress, the coefficient that we will get, we will denote this as S suffix D. Why D? Because the displacement, the charge displacement that we are doing is 0. And 0 is a constant, right? Right, any questions? So SD and SE, they are not same. We have discussed SE in the previous slide. Now we are discussing SD, right? So they are not same. So what happens is when we are stretching, we will have to apply a force, we'll have to make an effort to stretch it, right? And there are the opposing forces that will happen or that will be appearing in the material will be because of two reasons. One is because of the mechanical structure of the material itself, and second, because of the charges that are developing. I'm trying to stretch, the charges are developing and it is going to try to pull towards each other. So I'm going to make an effort, and that effort that I'm making is going to be stored both as mechanical energy in terms of the material deformation, or I shouldn't say deformation, the material elongation that it's going to undergo, as well as the electrical energy in terms of the charges that are accumulating, or the delta charges that are appearing on the two surfaces of the plate, right? So we'll hold on to this thought and then look at the other condition. Again, going back to SE, right? So this we discussed already in the previous slide, right? That we are going to apply a force, same force. Let's say we are applying the same force in the same direction, right? We are applying the same force in the same direction, and only difference is we have shorted these two terminals. So this is a short circuit. So the first one is open circuit. This is short circuit, right? Not a big deal. And we do a lot of open circuit and short circuit analysis in amplifiers, right? So similar to or amplifiers or two-port networks, or to do the network analysis to derive the network parameters. I think you guys must be very well aware of this open circuit and short circuit terminologies, right? So under this condition, we said that only mechanical energy will be stored and no electrical energy. Why? Because we have shorted the two faces of the material. The electrical energy kind of gets dissipated. There's no electrical energy that is stored at all, right? And under this condition, if we were to plot strain as a function of stress, right, then the coefficient that we will obtain is compliance at a constant electrical field E. So now let me ask you this question, and you guys must answer this to me. If you have understood this, you should be able to answer. So for the same material, which coefficient do you think should be higher, SD or SE? Which one should be higher? Anyone?
SD. Hello,
SD.
sir.
Yeah, SD. So SD. That's your answer, right? So who is this? Can you please? Okay, Shubham. So Shubham, can you explain why do you think SD should be higher?
So if you look at the equations, then and if you look at specifically actuator equation, then we can try to convert. So we'll try to find this SD. So that will be SE plus something in the terms of electric.
So one correction, Shubham, sorry to interrupt. One correction. So we are not talking of this as an actuator or a sensor yet in this, right? We are just trying to study the material under, and what are we trying to study? We are trying to study the mechanical property or the mechanical coefficient of this material under two different electrical conditions. And in that context, I understand why you are saying this is an actuator, because we have discussed this, right? And then we said that because it's an actuator, we are talking of this guy here. I understand what you are saying. But in this context, I'm saying that, yeah, we are not talking of this as a sensor versus actuator. We are just trying to study the material under two given electrical consideration. So now please go ahead and explain why SD should be higher.
So, but this relation that this strain is equals to SET plus D times E. So, if we try to like manipulate this equation and get like something times D, then you will see that SE plus something is going on. So that is why I said that.
Okay, so
SE
someone
should.
else, yeah, someone else wants to take a shot at this, and please try to think
Yes.
physically. See, it's very important, right? In engineering, I keep telling this. If you guys are going to take up a hardcore engineering in your career, right, it's extremely important to get an intuitive understanding. See, in the engineering, like if you're working as an electronics engineer, right, and let's say you are in a meeting with 5 or 10 different people, you are not going to talk to them based on equations. Even when you are discussing very complicated analog circuits or whatever be it, right? We talk mostly from a gut feel, mostly from an intuitive feel. So please try to develop that, and please answer this from an intuitive, like what are we trying to do? We are trying to stretch this material, and what are we going to face? The material is going to oppose it, right? So can you think in that terms, right? And we also
Yes.
describe what is compliance, right? Yes, go ahead, Nayan. Nayan or somebody else was also trying to give an answer. Nayan, please go ahead.
No, can I try?
Yes, go ahead. Okay, Shakshi, you first.
Yes, so in the when it's open circuit, there is some internal electric field present which
Mhm.
opposes the force we are applying. So due
Right.
to that reason,
No, so which one is higher? So what is your answer? SD is higher?
I'll say SE is higher because it is more compliant because there is no internal electric field present
Excellent.
here.
Excellent, Shakshi. Excellent. Great. So she has hit the nail on the head. So see, what do we mean by compliance? We discussed, right? Compliance is how the material is responding to the external information. Like for example, to explain the concept of compliance, I talked about human behavior also, right? I talked about how the class is going to behave, right? If let's say a few students are actually following the class, then I will say that this particular student is very compliant, meaning he or she is attending the class, attentive in the class, understanding, and taking the information as I'm trying to present it. Whereas there will be students, right, who will be non-compliant, meaning they are stiff, they are not attending the class, not attentive or whatever, right? So if you see these two conditions, right, under these two conditions, the same material will actually show different compliance. And what Shakshi mentioned is the one on the left hand side, this configuration will be less compliant. Why it is less compliant? Because when you are applying the force, not only is the material trying to oppose it, but also the charges that are developing, right? That is also trying to oppose it, right? So we will find it harder under this condition on the left hand side, we'll find it harder to stretch the material, right? That means this material is stiffer, which means the compliance coefficient must be smaller. It is less compliant to the external force that we are giving. So the answer is yes, SE should be higher. The compliance matrix S suffix E is higher than S suffix D. Understood? Any questions, doubt? Understood, right? Okay, cool. So now let's talk about the boundary conditions, mechanical boundary conditions, right? So again, we have the same material and we apply a battery, which we have shown, right? And what will happen if we apply the battery? We have discussed this, right? We are applying the battery. Please note the direction that the external battery we are applying. So the external field is in opposite direction to the polling direction, right? Which means the material will actually become shorter, right? This length that we have here this length will reduce, right? And that's what I've kind of tried to show by the box, right? So what is this condition? So here I'm saying stress is constant and I can say T is equal to 0. Now, why am I saying stress is constant and T is equal to 0? Why am I saying that? Somebody can say, sir, but the material has deformed, right? And so basically there is strain, for sure there is strain. We can see that the material has deformed and the length has kind of reduced, right? So there is strain. So if there is strain, there must be stress, right? So the answer to this is no. There is no stress in this condition. The reason is this is a new equilibrium under the condition of this new, I mean the battery that we have placed here. Yes, the material is deforming, but it is not under stress. It is deforming by virtue of the material property itself, meaning the internal crystal structure is getting, it's modifying, it's getting modified by the external electric field to ensure that it reaches an equilibrium state, right? When do we say that the material is under stress? When do we say that, so let's say during the exam time, we say, bhai, bahut stress hai, right? Why are we saying that, you know, because that is not the normal condition that you find yourself in day-to-day life, right? During exams, you have to work harder, study harder, look at, you know, the assignments or whatever, right? I mean, so that, you know, you can prepare well, right? So that is stress. Anything which is not normal or in your equilibrium state, we will call it stress. So here, what has happened is essentially the material is moving to a new equilibrium state based on the external environment. So it is not under stress, so to say, just that the environment has changed and it is just adjusting, right? For example, if it's winter, you know, you just wear some more clothes, right? Warm clothes, right? And that's about it, right? You are not, your equilibrium state is getting changed, but you are not under stress, so to say. So here it is important to understand that even if there is strain, the stress is 0, right? So under this condition, if we were to measure the permittivity, right? So permittivity is what? An electrical domain characteristics, right? If we were to measure the permittivity, we will denote that permittivity as epsilon suffix T, right? Why T? Because the stress in this is constant. Stress is constant. And as I said, zero is a, you know, constant number, right? Right. So instead of, you know, this configuration, so let's say what I can have is, let's say this is lying on ground, let's say, right? And I have another weight, let's say another mass lying on top of this, right? And I were to do the same experiment. I'm trying to measure the permittivity in this condition. So how should I denote that permittivity? I repeat, just like so far we discussed, in this condition, I'm measuring the permittivity at a constant stress T equal to 0. And that's why I'm denoting this as epsilon suffix T. What I'm saying is, let's say the material is lying on ground, right? And we have, it's not glued or anything, right? It's not, you know, but then we have a mass M lying on top of it. And in this condition, if we were to measure epsilon, how would we denote it? Will it be epsilon T or epsilon something else? Any guesses, guys? And just
Epsilon
to repeat,
T.
epsilon T.
Yes.
Yes, Nan, epsilon T, right? Correct. Why do you say that, Nan? Just kind of explain your answer, please.
So you said that the stress is constant because when
Right.
we put a mass on the system, the stress will be constant throughout. That's why
Right.
I said.
Right. Right. But then which epsilon do you think will be higher? In the first place, whatever we measured, or the new epsilon? So basically, let's say I will say epsilon T0, and the second one, let's say we are measuring is epsilon Tm. So which do you think will be higher, epsilon T0 or epsilon Tm? T0 means permittivity measured at constant stress of 0. And the second one is permittivity measured at constant stress of, whatever, because of this mass m that we have kept. So which one do you think will be higher?
Epsilon T0 will be higher.
That will be higher. Who is this?
Sakshi.
Oh, hi. Okay, Shakshi. So can you explain why epsilon T0 will be higher?
So if a mass is placed, the electric field inside will increase, right?
Mm-hmm.
So the permittivity will decrease.
Okay. In the previous thing that you answered, right? When we talked of compliance, right? You looked at from a physical point of view, which is going to be stiffer, right? So here, so if we have, so basically, please read this portion, right? In the when we have actually, yeah, in this we have both electrical and mechanical energy stored, right? Because the material is also getting modified, right, or deformed, right? So from that point of view, if we have a mass m, can you explain maybe a little bit more, in physical terms? So what happens is, if we have a mass m on top of it, right? Will the deformation be more or will the deformation be less because of the electric field?
Sir, it will be more.
The deformation due to the electric field will be less in this case.
In this case, meaning which case?
Yes. When the mass m is placed.
Okay. The deformation in the second scenario, you are saying will be more or less. You said less. Less. Why should it be less?
Because it is getting deformed due to the stress, due to
No.
the
So
constant stress
so
which is
Sakshi, let's
being
look at it
applied.
like this, right? See, because of the external field, the material has deformed. It has reduced its length, right? Right. And then on top of it, we are putting another mass, right? That means we are
Yes.
actually compressing it further, right?
Yes. So
Yes. Go
so
ahead.
it will not be, so the deformation due to electric field will be less here, right? Because
Yes.
it is getting deformed due to the mass also.
Yes. So basically what Sakshi is saying, so let's look at it like this, right? So when we place the mass, we are trying to compress this material, right? Which means the charges that will appear because of, let's say the battery is not there, the charges that will appear, right, will be such that it is going to oppose the deformation because of the mass, right? Right. So what happens is, now that we have a battery, these guys will not be there. These guys will not be there, right? But the material has deformed, right? On top of it, now we have, so the electrical energy. So basically, when we talk of electrical energy stored, right, we call it as epsilon, half CV square, right? And C is nothing but whatever that epsilon A by dV square, right? Right. So the point is, we have to look at under which condition the electrical energy that is stored is more. Is it under, this condition when the mass is actually placed, or when the mass is actually not there? We have to think from that perspective. If the electrical energy, So I would leave this. There will be assignments also given, but this I'm not giving it as there's too simple a stuff to give an assignment. But we will discuss this again. Please think about this. Which one will be more, epsilon Tm or epsilon T0, right? And let us proceed and look at the second condition. Okay, so the second condition is we have the same material, but this side is glued. We are not going to allow the material to deform, right? And under this condition, we are applying an external voltage source. So under this condition, we are saying the strain is constant, right? And that is fair to say, right? There is no strain. We are not allowing the material to kind of increase or decrease or whatever, right? We are ensuring that the material remains as it is, right? And under this condition, because there is no strain, we can say that there is no mechanical energy stored, right? And under this condition, if we measure the permittivity, we are going to denote this as epsilon subscript S. Is this clear? The only difference between this guy and this guy, that this side and this side, is I've glued the material such that there is no deformation in the material. And under this condition, if I'm applying a battery, I am going to refer epsilon S. I'm going to refer this as epsilon S, right? And then going back to the same question, is epsilon T higher or epsilon S higher? Is epsilon T higher or epsilon S higher? So going by that same explanation that we gave, right? In the first condition, we have both electrical as well as mechanical energy stored, right? So the energy that I'm going to, or the energy that is going to be provided in this condition, right, by the battery, that will be higher. Epsilon T will be higher because we are storing the energy not only in electrical form, but also in mechanical form, right? So just like we talked about compliance matrix under, constant. So this guy, right? We talked about SD as well as SE, right? Under different electrical conditions. So similarly, we can talk of permittivity under two different conditions. When in one case, when the material is free and we can store both electrical as well as mechanical energy, whereas in the second case, it is clamped. So we are not storing any mechanical energy, only electrical energy is getting stored. So by that virtue, we can say that this guy will provide a bigger capacitor. It will behave as a bigger capacitor. A capacitor is what? It is nothing but it can store charge or it can store energy in it, right? It's like a reservoir, right? It's like a if you want, like we store water in a bucket, right? So the capacitor is like that, right? So the more water a bucket can hold, the bigger it is, right? So basically, in this case, because this material can store more energy, both mechanical as well as electrical, we are saying this guy has higher capacitance. And because it has higher capacitance, where is that higher capacitance coming from? Because the material and everything is same, right? So it is coming from the fact that the permittivity of the material is different from this condition and this condition. Any doubts? This should be clear, right?
So can you repeat it again?
Okay. So see, let's go back to the first one, right? Because the first one is probably easier to understand, right? Which one was easier to stretch, this side or the left side or the right side? So let's call it left, L. Which one was easier to stretch? Sorry. So as Sakshi rightly pointed out,
Right one. Right one.
Right one, correct. The reason why the right one is easier to stretch, because we are giving an external condition so that whatever extra charges would have developed and tried to oppose, right? Those I'm kind of eating away. I'm not allowing those extra charges. So it's like this, right? I mean, if let's say there's a bunch of workers working in a factory trying to oppose the management, right? So if we ensure that there is no such worker trying to oppose the management at all, then of course, I mean, whoever is trying to oppose, let's say, is fired from the job, even before, let's say, they can form a group, right? So then we know that the factory or the set of workers will be more compliant, right? So this, under this condition, the right one, this is a more compliant condition. Whereas in this case, not only is the material trying to oppose, but also the charges that are developing, that is also opposing the external, whatever we are trying to do, right? So the key point to note here is, in this condition, in the thing that is on the left hand side, we have both mechanical energy as well as electrical energy that is getting stored. And that is the reason this guy is less compliant. Mechanically, it is less compliant, right? However, let's flip it and look at it from an electrical point of view. So when you're looking at it from an electrical point of view, so epsilon, so when we are talking of the energy stored in a capacitor, we say we said that, right? It is half CV square, right? This is the energy that we say, right? Right. So here on the left hand side, whatever we have, we are actually storing the energy in two forms, right? Both as a mechanical energy, because we are allowing the material to deform, we are allowing it to go up and down, as well as electrical energy, right? Right? And we have discussed what will happen, how the charges are going to accumulate, whether the charges are going to increase or decrease, that also we have seen, right? So essentially, we are storing the energy in two forms, mechanical as well as electrical. So the energy that we are storing, we can think of it, we are storing higher energy in the same piece of material, right? In this case, because we are not allowing the material to kind of move at all, there is no mechanical energy that is getting stored, right? Only energy that is getting stored is electrical energy, right? So basically, the same material on the left hand side has got higher ability to store energy, whereas on the right hand side, this guy, it has got lower capacity, right? Lower capacity. It can store energy in only electrical form. The mechanical, we are kind of, we are kind of killing it. So if we think in terms of half CV square, or energy is proportional to the permittivity, right? We can say that, right? Energy is proportional to the permittivity, right? So which one we can say will have higher permittivity? That is the one on the left, right? So epsilon T is actually higher than epsilon S. Understood?
Yes.
Okay. So we'll probably stop here. Okay, this is a good point to stop. We are going to talk about the different forms of the equations tomorrow. This is a good point to stop. But please, again, so that things are going to get a little bit more involved. We'll see the 4 forms of the equations, and we'll try to find the relationship also. So things are going to get more involved, but it's very important to understand intuitively what we are discussing. Otherwise, it will, we'll probably lose track. Okay. So any questions today so far? I have kind of intentionally gone slow for the last couple of days because it's very important to understand the basics here. I mean, equations and all that is fine, we will remember, but it's important to understand the physics. Okay. Okay, guys. So have a good day. I'll stop the meeting. Okay, thank you.